In this problem, we have a pharmaceutical company that's developed a new cancer drug, and it's about to launch this drug commercially. And so the first thing we want to do when we have a problem like this is to draw a timeline. So we expect that this cancer drug is going to generate $100 million of profit every year for the next 14 years. So in year 1, we receive $100 million. In year 2, we receive another $100 million. And this is going to keep going until year 14. At the end of year 14, we assume that this drug is going to go off patent, and generics are going to drive the profitability of this drug to 0. And so the question is, what's the value of this sequence of cash flows to us today in time 0? And so there's 2 ways to calculate the NPV in this question. There's an easy way and a hard way. The hard way would be to discount each one of these cash flows individually to time 0, and then sum the resulting discounted cash flows together. But one thing we can notice is each one of these cash flows actually has the same magnitude. And so these actually forms an annuity. And so we can use our annuity formula. So recall that the present value of an annuity is equal to x over r, where x is the magnitude of each cash flow, and r is the discount rate, which in this example we're told to assume is 10% per year, multiplied by 1 minus 1 over 1 plus the discount rate to the capital T, where in this case capital T is 14. It's the number of cash flows we receive. And so now we have everything we need to calculate the present value of a sequence of cash flows. We can just plug it into this formula. And so when we do that, we get the present value is equal to 100 over 0.1 times 1 minus 1 over 1.1 to the 14. And when we compute this expression, we find that the present value is equal to $737 million. And so these shortcuts, like the annuity formula and the perpetuity formula, we're going to use these formulas throughout this course. And they're very useful for calculating the present value of large sequences of cash flows.